In this demo, I'm going to show you how deadlocks are created. First of all, I'm going to set up a small scenario that is going to create a deadlock. We'll look at the locks involved and the hierarchy of locks. And finally, we'll look at a deadlock graph to get some more insight into how to fix the problem in our applications. The first thing I'm going to do is I'm going to turn on Profiler to capture a deadlock graph that we're going to create. And I don't recommend using Profiler in a production environment, but for the purposes of this demo, this is the easiest way to do it. So I'm just going to organize my columns a little bit here, because we'll need the text data column in a second. Okay. So next step is to set up the scenario. Now I've got a script here that creates two tables and inserts a single row into each one. Now I have two different scripts here that do update operations on each of the tables I created. And what I'm going to do is I'm going to record the session ID, because in the lock query that I'm going to use, it's going to show us the session ID. It's not going to show us, connection A and B. So let me just write these down so it's easier to follow. Okay, so in connection A, what I'm going to do now is I'm going to open a transaction, and then I'm going to update the single row in the first table. And when I go over and look at the locks, you can see that on 57, that was the right one, right? Yep. You can see we have a database shared lock, a table intent exclusive lock, a page intent exclusive lock, and finally an exclusive lock on a row. If we go back and look at connection B, we'll do the same sort of thing except on the second table. And noting that our transaction in both connections is still open, which is how we're able to look at these locks here. So on connection 58, session 58, do the same sort of thing: database shared lock, table intent exclusive lock, page intent exclusive lock, and row exclusive lock. Now we haven't actually created a conflict yet. All we have are two transactions that are open. In order to create a deadlock, we have to have each connection asking for resources from the other connection, and we haven't done that yet. So let's go back to connection A, and what we're going to do now is run a select star from the second table, which connection B has currently updated, and it's holding a transaction open. So when we execute this, SQL Server is going to have to wait behind the exclusive lock on the table that's being held by connection B. So this is not a deadlock. This is called blocking, and blocking is perfectly normal. In this case, we're waiting indefinitely because I've intentionally held the transaction open just for the purpose of the demo. And you can see how the general best practice of trying to keep your transactions as short as possible is a good one. So if the transaction in connection B was very short and it committed now, this would unblock and it would proceed. If we go and look at the locks, you can see that before I executed the select statement, all our locks were granted. When I run the query again, I'm going to see that now we have to wait to read the row that is exclusively locked by the other session. And you can see this by looking at the RID for both of the locks. So still we haven't created a deadlock. What we have to do is go back and create the same sort of scenario on connection B. So connection A has locked first table, and it's asked for resources from second table. Connection B has locked resources on second table, and now we're about to ask for resources on first table. This is what creates the deadlock. So the deadlock monitor, which is a process in SQL Server, will pick it up, but not immediately. So what I'm going to do is, after I run this statement, I'm going to quickly flip back to the lock query and run it, and hopefully we can see all of the locks as they are before the deadlock monitor picks up that there is a problem. So I'm sorry, it's going to flip really quickly here, but alright, let's go. So I'll run this, flip over to the lock, run that, and we'll analyze what happens. Okay, unfortunately I was not quick enough, so that's kind of unfortunate, but we will be able to see the locks in the deadlock graph a little bit later. So as you can see, what happened was the transaction on connection B was killed by the deadlock monitor. In other words, it was chosen as the deadlock victim. And what happened on connection A is that our select statement was unblocked and we got our result back. Now, you might notice that this returned the result of 1, and that's because when the process connection B was deadlocked, it was killed, and what happened was the transaction rolled back. So it's as if this never happened, and we get the value 1 back. So we actually still have an open transaction here, but that's okay, I'll just leave it. And we should have captured a deadlock in Profiler here. Now, sorry it's a little small, but you can see that this one here, our select from first table, was killed by the blue X, and you can see the other process here. The square boxes show us the resources that were requested by both and how they were requested. So you can see the request mode means this process requested this resource to read it, because it's shared lock, but this process already owned a lock in exclusive mode. And the same thing here. So second table was requested, but it was exclusively locked by this one, which I believe is process B. So in this case, it's nice in that it gives us the actual table name. Sometimes it won't, and you'll have to use this object ID to go back to the metadata tables to figure out what actually was locked. So now what I'm going to do is, well, first let me just say the deadlock graph here is really nice to be able to visualize what happens, because sometimes it can happen with more than just two tables. It could happen within the same table. It could involve more than two things or more than two processes. So I find this really helpful to be able to visualize what's going on. Now, the deadlock graph itself is actually driven by XML, as you can see in the text data column here. So what I'm going to do is I'm going to extract the text data column and just save this as essentially an XML file with a special extension on my desktop. Now, if I open that file directly in Management Studio, it's just going to show me the same deadlock graph. What I'm interested in, though, is the XML behind it, because it gives us more information. So what I'm going to do is select the file, but I'm going to open it with the XML editor. And you can see there's a lot of information here that the deadlock graph consolidates for us. You can see things like the resources, how long it's waited, all the locking modes, etc. One of the most interesting things is found in the process list, and if I scroll to the right here, you can see it gives us a whole lot of information to be able to track back to where it occurred. And the most important thing, hopefully, is it captures the application name automatically, which is great because you may have queries from different applications. You may have the same query from different applications, and you may find that there are certain combinations of applications that don't play well together. You can also see who is doing things and the isolation level. So I hope this has been informative, and hopefully you understand more about deadlocks and how they occur now. Thanks for watching.